Today, the colligative property we're going to focus on is the vapor pressure of a solution. And as we talk about the colligative properties, recall that all of the colligative properties are going to be related to that of the pure solvent. There's just going to be some sort of difference with them as we look to the effect of adding that solute. So what we're going to look at today is Raoult's law, which is looking at the vapor pressure, which lowers of a solution. So recall, for a vapor pressure, if you were to consider that you have a sample here, and then it's either a liquid or a solid, so whatever phase this is, liquid or solid, we're looking at the pressure of the vapor that's right above the solid or liquid interface that we're looking at. So it's the pressure of the molecules that are going up into the gas phase, and some of these molecules will be going up in the gas phase, and some of these will be going back into the liquid or solid phase. So again, the vapor pressure is the pressure that's exerted by this vapor that's right above that interface. So there's two different types of solutes. There's one where we have a non-volatile solute, and this is whenever we have negligible vapor pressure. And this is whenever we have a solid or a liquid. And so what we'll see is we have one set of rules for dealing with non-volatile solutes, and then we'll deal with volatile solutes in a slightly different way. What we mean by non-volatile means it's not overly reactive. You may hear someone as having a volatile personality, meaning they get angry or they have extreme emotions out of nowhere, so they're quite reactive. So we will also explore volatile solutes as well. And what we'll look at here are cases of liquids and liquids, so a liquid solute and a liquid solvent. And then we'll see how to deal with this. And so let's go ahead and look at Raoult's law. So Raoult's law states that the pressure of the solution is equal to the pressure of the solvent times the mole fraction of the solvent. Okay, so we're going to have to be given enough information that we either have the pressure of the solvent and the mole fraction of the solvent, or we're given some amount of information that we are able to solve for the mole fraction of the solvent. So the general problem-solving strategy for these will be is let's make a list of all of our variables and things that are given to us, and then rearrange the equation to solve for our unknown. So our first example, let's go ahead and look at a solution with a non-volatile solute. So here we have 1 mole of glucose and 15 moles of water at 25 degrees Celsius, and we want to end up finding the mole fraction of water, which is our solvent, mole fraction of water, and we also want to find the pressure of the solution and then the change in pressure. So what happened to the pressure? So we already said that for colligative properties that the vapor pressure of the solution is lower, so we will compare the vapor pressure of our solution to that of the pure solvent. So as we're reading this problem, you should recognize that glucose is your solute and that water is your solvent. If we want to find the mole fraction of our solvent, what we'll have to do is we'll find the moles of our solvent and divide by the moles of solvent plus the moles of solute. All right, so in this case, we have 15 moles of water all over. Well, we have 15 moles of water plus 1 mole of glucose. So that's a total of 16 moles. Recall that the mole fraction is dimensionless, so those units cancel out. And we'll have that fraction of 15/16. So we know the mole fraction. We're also given the vapor pressure of the solvent is 23.76 torr. So using Raoult's law, which says the pressure of the solution is equal to the mole fraction of the solvent times the pressure of the solvent, we can plug in, well, we have our 15/16 here times the 23.76. I guess we should keep in mind sig figs. This was 15.0 and 16.0. So the vapor pressure of our solution is 22.3 torr. Okay, so if we want to find the change in pressure, what we can do is we can take the pressure of our solution, so that's the final pressure that we're looking at minus the initial pressure, which would be the pressure of our solvent. And we see that this was lowered by 1.5 torr. So a few things I want to point out is glucose is a covalently bonded molecule. So that means it does not dissociate. So we didn't have to deal with a Van't Hoff factor of I. So let's go ahead and look at whenever we do have to deal with a Van't Hoff factor. So a Van't Hoff factor is what we talked about earlier with an ionic substance that will dissociate into two parts. So what we'll do is we're going to look at an example now of, again, another non-volatile solute, but now we have sodium chloride as our solute. And we know this is an ionic compound, and we will assume that this dissociates completely, which means that I is equal to 2. So since we're going to assume complete dissociation, that means that from our solute, we have 1 mole of sodium chloride. Well, if it dissociates into sodium ions and chloride ions, we'll have 1 mole of sodium ions and 1 mole of chloride ions. So as we start to solve this problem, we're going to have to find the mole fraction of water, the pressure of the solution, and the change in pressure. So let's go ahead and find this mole fraction of water, which is our solvent. So we have 15 moles of water, just like the previous problem. And again, we have 1 mole of solute, but since this is an ionic solute, it dissociates. So our total moles will not be over 16. It will actually be over 17, because this broke up into sodium ions and chloride ions. So we end up with a mole fraction here of 15/17. The pressure of the solvent was given to us in the problem again. That's 23.76 torr. So recall that Raoult's law says the pressure of the solution is equal to the mole fraction of the solvent times the pressure of the solvent. So plugging in, we have 15/17. So we better keep in mind sig figs. 'Tis the season to get siggy. Times the vapor pressure of water. And then what we'll find is the pressure of the solution is equal to 21.0 torr, which means that delta P here, pressure of the solution minus the pressure of the solvent, is equal to negative 2.8 torr. So we've looked at two different non-volatile solutes, one where it didn't dissociate and one where it did dissociate. So now the next thing that we need to do is, well, let's look at something whenever it is a volatile solute, whenever we have an appreciable vapor pressure. So whenever we have an appreciable vapor pressure, what we're actually going to do is we are going to use Dalton's law. So Dalton's law is looking at the sum of the partial pressures. So we're going to calculate pressure of A and pressure of B using Raoult's law. So if the pressure of A is equal to the mole fraction times the pressure of the pure solvent, and that's what this degree sign here, this means the pure solvent. Because what we'll see is whenever we're mixing two liquids, they could both technically be solvents, but we're going to be looking at the mole fraction. So one of them may be considered the solute and one of them may be considered the solvent. So we're going to have to use Raoult's law twice. So we have P sub B is equal to the mole fraction of the solvent times the pressure of the pure solvent. So let's go ahead and look at this. So for this problem, we're going to mix two similar organic liquids, benzene, which has a boiling point of 80.1 degrees Celsius, and toluene, which has a boiling point of 110.6 degrees Celsius. Pure benzene has a vapor pressure of 96 torr, and pure toluene has a vapor pressure of 30.3 torr. We're going to mix them in a 1-to-1 molar mixture where X, so the mole fraction is 0.5, and we want to calculate the vapor pressure of the solution. One of the things that I do want to point out and make you remember from intermolecular forces is if you have a higher vapor pressure, that means you're going to end up having a lower boiling point. So higher vapor pressure, lower boiling point. So now what we're going to do is let's go ahead and come up with an expectation for this problem. Where should our vapor pressure end up falling? Well, our vapor pressure should be somewhere between 30 and 96. It needs to be between those two values because this is what we're mixing, so we can't go higher than either of them, and we can't go we can't go higher than the top end, and we can't go lower than the bottom end. So here, recalling Dalton's law, we'll say, well, the total pressure of our solution is equal to the pressure of benzene plus the pressure of the toluene. So then substituting in with Raoult's law, this is the mole fraction of benzene times the pressure of the pure benzene plus the mole fraction of the toluene times the pressure of the pure toluene. So here the mole fraction is 0.5. So we'll take 0.5 times the vapor pressure of benzene, which is 96. Plus 0.5 times the vapor pressure of the toluene. And our total pressure of our solution is 63.2 torr. All right, so that concludes our discussion on Raoult's law.